Hello and welcome to Scholar Edu. This is our JAMB or UTME prep series where we provide relatively detailed solutions to the UTME questions. And in this recording, we are looking at the UTME questions for physics for the year 2016. This is the first part of the recording. We are going to look at the first 20 questions for this year. Before we continue, please don't forget to subscribe to our YouTube channel, like and share our content. You can also visit our website at scholarlive.com to practice the JAMB exam and modular quizzes for free. Okay, first question here on measurement. What is the least possible error encountered when taking measurement with a meter rule? That is 0.5 millimeter. So the accuracy of a meter rule is 1 millimeter or 0.1 centimeter. The least possible error, okay, that can be obtained from the use of a meter rule to take measurement is half of the smallest reading on the meter rule, which is 1 millimeter. So half of 1 millimeter, that is 0.5 millimeter or 0.05 centimeter. That is why if you take a measurement with a meter rule, let's say you measure something to be x millimeter, you can write that measurement as x plus or minus 0.5 millimeter. It means that let's say that the actual length of that thing is 10 millimeter. If somebody records it or reads it as 10.5 millimeter, that would still be acceptable. That is like saying 10 plus 0.5. And if they read it as 9.5, that's 10 minus 0.5, that will still be like an acceptable reading. Okay, so it will still be within the range of acceptable readings for the measurements with the meter rule. Okay, so the least possible error encountered is 0.5. Next, on electromagnetic induction, the electromotive force in the secondary winding is, so as you can see, this is the primary winding and this is secondary winding. Now if you look at the number of turns, the turns in the secondary winding, you see it is greater than you have in the primary winding. So that means that now the electromotive force varies directly as the number of turns or windings. Okay, so since we have a greater number of winding on the secondary here or on the output here, that means that the electromotive force is increasing. Okay, next, on work, energy and power. If a pump is capable of lifting 5,000 kilograms of water through a vertical height of 60 meters in 15 minutes, the power of the pump is, okay, the formula for power is energy over time. Okay, and here the energy here is going to be the work done in lifting the water, which will be equal to the weight of the water times the height to which that water was lifted. And the weight of the body is given as what? Mg, the mass of the body times acceleration due to gravity. So you have the weight mg times the height over time. Now from the question, we have the mass to be 5,000 kilogram. Okay, we have the height as 60 meter, the time is 15 minutes. We need to convert that to seconds. Okay, we need to convert it to seconds. How do you convert from minutes to second? 1 minute is 60 seconds. So we are now have 15 minutes. That's going to be 15 times 60 seconds. So that will be 900 seconds. The acceleration due to gravity, as we know it, okay, is 10 meter per second square. Sometimes it is taken as 9.8 meter per second square. But where it is not stated, you can take it as 10 or as 9.8. Okay, then you can work with either of them and see what you get. So here we have mass 5,000 times g, acceleration due to gravity, that's 10 times the height, which is 60, divided by the time, which is 900 seconds. So by the time you multiply all of this and divide by 900, you'll be getting 3,333.333. okay, we can neglect what we have here. Now we want to write this in standard form. This 3333, we want to write it in standard form. Now this is like 3,000, right? 3,000. So I can write this as 3.3 times 1,000. Okay, since this is 3,000 something, I can write it as 3. I'll just put the point here. Okay, I'll just put a point here. 3.3 times 1,000, and 1,000 is 10 raised to power 3, meaning 10 times 10 times 10. So I have this as 3.3 times 10 raised to power 3 joules per second, which is the unit for power here. Okay, joules per second, you can write it this way, or you can write it as Js raised to power minus 1. You can write it either ways. But if you are using negative indices, like negative index like this, negative powers, you don't use the slash. Next, on its calorimetry, calculate the temperature change when 500 joules of heat is supplied to 100 grams of water. we know that the quantity of heat, okay, that will be supplied to the water is going to be equal to mc delta theta, where m is the mass of the water, c the specific heat capacity of the water, and this delta theta is the change in temperature of the water. Now in this question, 500 joules of heat was supplied. That is our q. We've been given q here. Okay, the mass of the water here is 100 gram, but we need to convert it to kilogram. Why? Because the specific heat capacity that we're going to use, if you look at the unit here, it is joules per kilogram. So it has kilogram, it's just kilogram here. Our unit has to be balanced. You cannot be using kilogram together with gram. Okay, so we have to balance the unit. So how do we balance the unit? We convert from gram to kilogram, and we have 1000 gram is equal to 1 kilogram. So to convert from gram to kilogram, we divide by 1000. So here you have 100 grams divided by 1000, and that will give you 0.1 kilogram. So that is the mass of that water in kilogram. Okay, now from this formula here, we are going to make this change in temperature, which is what we are looking for, the temperature change. This change in temperature, we will make it the formula. How do you make it the formula? We are going to divide both sides here by mc. So I'm going to have q over mc is equal to mc delta theta over mc. So mc will cancel mc on this side. I'll have just delta theta is equal to, on this side, q over mc. So the q here, quantity of heat supplied, is 500 joules, as we have from the question. 500 joules of heat is supplied. So you have 500 divided by the mass of the water is 0.1, okay, multiplied by the heat capacity of the water, which is 4200. So here we have 500 divided by 4200. That's 0.1 times, sorry, 0.1 times 4200 is 420. So I'm going to have 500 divided by 420, and that is 1.2 degrees Celsius. So this is the rise in temperature. Okay, and we say it is a rise in temperature because this is positive. Next, for nuclear physics, which of the following particles cannot be deflected by both electric and magnetic field? That is a gamma ray. Okay, the gamma ray is neutral, and as such, it is not deflected by electric and magnetic field, unlike the alpha ray and the beta the alpha ray and the beta ray. Okay, both of them are charged, so they are deflected by an electric field and a magnetic field. But the gamma ray is neutral, just like the X-ray. It is not deflected by magnetic or electric field. Next, on matter, under which of the following conditions do gases conduct electricity? Gases can be made to conduct electricity at very low pressure and high potential difference, high voltage. So low pressure and high voltage, this is the condition that is required for gas to be made to conduct electricity. Next, on optics, dispersion occurs when white light passes through a glass prism because of the white light consists of 7 colors. Okay, the Roy beef: red, orange, yellow, green, blue. We have indigo. Okay, then violet. Now these colors, they move at different speed. Okay, in this medium here, this glass prism here, which is the reason why they emerge separately. Okay, this is what causes the separation, the dispersion of that white light, because of the different speed of the colors in the glass. Next, we have a diagram here. The question is, calculate the EMF of the cell in the above circuit if its internal resistance is negligible. And if you look at this circuit, we have 2 resistors connected in parallel. Okay, and the current flowing through this circuit is 4 ampere. So what we need to do here is find the effective resistance for these 2 that are in parallel. And when you have 2 resistors in parallel, like let's say R1 and R2, we say that the effective resistance, let's say it is R, will be given by 1 over R is equal to 1 over R1 plus 1 over R2. Okay, that's what it will be, 1 over R1 plus 1 over R2. This R is the effective resistance, and that's what we are looking for now. So this will be 1 over R1, let's say that is 3 ohms, plus 1 over R2, let's say that is 6 ohms. Then we take the LCM of 3 and 6, the denominators here, which here is 6. Then we say, what is 3 in 6? 2 times 1, that is 2, plus this plus that we have here. 6 in 6 is 1. 1 times 1, that is 1. So we have 2 plus 1 over 6 here. 2 plus 1, that is 3 over 6. If you reduce this to the lowest term, you are going to have 1 over 6, 1 over 2 rather. That's if you divide denominator and denominator by 2. So you have 1 over R is equal to 1 over 2. And if you compare both sides of the equation, okay, or you invert it, you are going to have R to be equal to 2 ohms. Now the formula for EMF is E is equal to I in bracket external resistance plus internal resistance. And since they said that the internal resistance is negligible, that means we are going to take it to be 0. We take this out to be 0, so we are going to have R plus 0, and that will just be R. So our EMF now is going to be IR. Okay, just external resistance. So the current is what, 4 ampere from what we have here, multiplied by R, which is the external resistance, and that's what we have calculated here as 2 ohms. So you have 4.0 multiplied by 2, and this will be 8 volts. So you have this to be 8 volts. That is the EMF of the cell. Next, on friction and viscosity, an object of mass 80 kg is pulled on a horizontal floor ground or horizontal rough ground by a force of 500 Newton. Find the coefficient of static friction. Alright, so we know that the coefficient of static friction is this, represented by this, okay, mu. It is equal to the applied force or the frictional force, okay, divided by the reactional force. Let's start with the reactional force. The reactional force is the weight of the body, okay, that's the reaction of the body on the surface of that plane. Okay, so it is equal to the weight of the body, and the weight of a body is given as the mass of the body times the acceleration due to gravity. Here we have the mass of the body as 80 kg multiplied by acceleration due to gravity is given here approximately as 10. So you have 80 times 10, and that is 500 Newton. Now, so we have this reactional force here, 800 Newton. While the pull force, the applied force here is 500 Newton from the question. Okay, from the question, pulled on this by a force of 500 Newton. That's the applied force. So you can now go back to this formula and say the coefficient of friction is equal to the applied force, that's 500 Newton, divided by the reactional force, which is 800, okay, which is 800 Newton. So you have 500 divided by 800, and that is 0.625. Now if you look at what we have here, this is all of these answers here to 1 decimal place. So we are going to approximate this to 1 decimal place. So this is in the first decimal place, this is in the second, this is in the third. So to approximate this to 1 decimal place, we are going to look at what is in the second decimal place. If you look at this figure here, it is not up to 5. Okay, so that means we are going to round it down as a 0. Okay, we round down as 0 and add it to this. This just means 6. So if that thing becomes 0 0, or we simply just omit it since they are like numbers after the decimal. So this is 0.6 approximately. We have our website at scholar.com where you could practice exams for free, the UTME exam and the post-UTME exam. It also features modular quizzes in physics, chemistry, and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at scholar.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next question on equilibrium and moment of forces. The diagram above shows Planck RS pivoted at its center of gravity O and is in equilibrium with the weights P and Q. If a weight 2P is added to P, okay, if you add another weight 2P to P, the Planck will be in equilibrium again by. So of course what happens is that this Planck is in equilibrium in this, okay, under this condition here. Alright, under this condition, if we now add another weight to this one, another weight to 2P to what you have already here, that means that this Planck is ordinarily, if it is since it's already in equilibrium like this, the equilibrium will be disturbed. Okay, this Planck is going to tilt to this side. It will tend to like tilt to this side, like to fall to this side. So we need to do something there. What do we do to keep it balanced? We are going to move this P nearer to O. Okay, now why are we doing that? Is because of what we call moment of force. If we look at, for this thing to be balanced, okay, the clockwise moment must counterbalance the anti-clockwise moment. The clockwise moment means this mass is going to be pulling this thing here, so it's also like moving it like this, okay, pulling it like this, and clock moves like this, the hand of the clock moves like this. So this is the clockwise moment. This is what is bringing about the clockwise moment. Why this is bringing about the anti-clockwise moment? Now the moment is actually the weight of this thing here times the distance between this thing and this thing. Okay, now what happens is when you add another mass here, okay, so the weight here multiplied by the distance between this and this. Now when we add another weight here, what's going to happen is that this now becomes, the moment here becomes greater. Okay, so in order to reduce that moment, what we'll do is we'll just move this closer to this. We will reduce the distance. Since we have added weight, the only thing we can do is to reduce the distance between this and this, so that it can now balance back again with this. So we are going to move P nearer to O so that the distance will reduce. Okay, and then we can balance this. This rule again can be balanced, or that plank RS can be balanced. Next on optics, a glass plate 0.9 centimeter thick has a refractive index of 1.50. How long does it take for a pulse of light to pass through the plate? We have the speed of light to be 3.0 times 10 raised to power 8. Okay, since the light here is going from air to glass, that is from air into the glass, then you have the refractive index to be equal to the speed in air, that's VA, over the speed in glass, denoted as VG. Now the refractive index we are given here to be 1.50, so we have 1.5 is equal to the speed of the light in air, which is 3.0 times 10 raised to power 8, divided by the speed of the light in glass, which is VG. Okay, so when you cross multiply this, if you cross multiply this, you are going to have 1.5 VG equals to 3.0 times 10 raised to power 8. To get the value of VG here, we are going to divide both sides by 1.5. So I'm going to have VG to be equal to 3.0 times 10 raised to power 8 divided by 1.5. To do this division, what I'm going to do is I'll just divide this part here. Okay, 3.0 divided by 1.5. You leave this 10 raised to power 8 as it is. Okay, 3.0 divided by 1.5 will give you 2.0. Then you have times, you bring this back, 10 raised to power 8 meter per second. Now recall that the formula for distance is equal to speed times time. Okay, so we have the distance that the light will move in that glass. Let's say that this is a glass, for example. Okay, a glass that is this thick. Let's say this is the thickness of the glass. It means that for the distance that the light will pass through will be equal to the thickness, of this glass. The distance through this glass is going to be its thickness. So we have the distance through the glass to be equal to the speed, okay, of light in the glass times the time. Because we are looking for time here, we're looking for how long does it take, the time. So we make T the subject of the formula here by dividing both sides by VG. So we have T to be equal to the distance in the glass, okay, the distance through the glass over the velocity of light, okay, in the glass. We are given the distance through the glass, or the thickness of the glass, as 0.9 centimeter. We are given in centimeter. We need to convert this to meter. Why? Because the speed, okay, here the speed that we are using here is in meter per second. So meter is what we have here. Our unit needs to be balanced. You cannot use meter with centimeter. Okay, you have to balance up the unit. So to balance the unit here, we would convert this one to meter. Okay, and how do you convert to meter? We simply divide. We are converting from centimeter to meter. You divide by 100. So if you divide the 0.9 by 100, you'll be getting 0.009 meter. And you can write this as 9 times 10 raised to power minus 8. Okay, 9 times 10 raised to power minus 8, because we have 3 zeros before the 9. Okay, and this is a number less than 1. So you have 9 times 10 raised to power minus 8 meter. Then we can now substitute this in this formula here, that the time will be equal to the distance through the glass, that's 9 times 10 raised to power minus 8, divided by the velocity or the speed of the light in that glass, which is 2.0 times 10 raised to power 8. That's what we calculated here. So how do we do this division here? We simply say, okay, divide the numbers, the number part of the standard form. So we have 9 divided by 2.0, that is 4.5. Then times, now we now have 10 raised to power minus 3 divided by 10 raised to power 8. 10 raised to power minus 3 divided by 10 raised to power 8. We are going to use our law of indices here. If I have 10 raised to power x divided by 10 raised to power y, that will be equal to 10, which is common here, 10 raised to power x minus y. That's what it will be. 10 raised to power x divided by 10 raised to power y will be 10 raised to power x minus y. So here I have 10 raised to power minus 3 divided by 10 raised to power 8. That will be equal to 10 raised to power minus 3 minus 8. So this will then be 4.5 times 10 raised to power minus 3 minus 8 is minus 11. So I have 4.5 times 10 raised to power minus 11. Next, on electromagnetic induction, the main purpose of the transformer in an AC radio set is to it is a step down transformer that is used in electronic devices like radio, and its main purpose is to step down the voltage. Next, on photoelectricity, the energy associated with the emitted photon when a mercury atom changes from one state to another is 3.3 electron volts eV. We have to calculate the frequency of the photon. So you know that the photon energy E is equal to HF. Okay, I want to find the frequency from here, so we are going to divide both sides by H. So we have E over H is equal to HF over H. H will cancel H on this side, and we have F to be equal to E over H. Now 1 electron volt is 1.6 times 10 raised to the power minus 9 volts. Okay, so the photon energy here for the mercury atom is 3.3 electron volts. So that will be 3.3 times an electron volt is 1.6 times 10 raised to the power minus 19. So 3.3 electron volts will be 3.3 times 1.6 times 10 raised to the power minus 19. Divide this by H, what we call the Planck's constant. Okay, the Planck's constant. The value of the Planck's constant is 6.63 times 10 raised to the power 28. So now at the numerator, 3.3 times 1.6 is going to be 5.28 times 10 raised to the power minus 19 over what we have here. Then we are going to divide this, just this. Okay, so we have 5.28 divided by 6.63, and that will give us 0.7963 multiplied by, we then use the law of indices on what we have here. Okay, we use law of indices here, so you have 10 raised to the power minus 19 divided by 10 raised to the power 28. Now if I have 10 raised to the power x divided by 10 raised to the power y using the law of indices, that will be equal to 10 raised to the power x minus y. Okay, so if we come here, this will remain as it is. 5 points, this divided by this is 0.7963 times, then this one using the law of indices will be 10 raised to the power minus 19 minus 23. This would then be 10 raised to the power minus 10 raised to the power minus 22. Okay, 10 raised to the power minus 42. That's minus 19 minus 23, that is minus 42. Now this is 0.76. okay, we are going to borrow a 10 from here and use it to multiply this. Remember that this is giving us 10 raised to the power minus 22 minus 42 rather. If we borrow a 10 again from this, that's like subtracting 10 from this, so we are going to have 10 raised to the power minus 43. Then we now use that 10 to multiply this one here, so we have is 0.7963 times 10, the 10 that we took from here, and this is already minus 42. So take 110 from it to have minus 43. So that 10 times this will give us 7.963. If you approximate this to one significant figure, we'll be having 8.0. Okay, because the next number, the first number emitted after the decimal is up to 5, so you round it up as 1 and add it to this. So this is 8.0 times 10 raised to the power minus 43 Hertz. Next question on nuclear physics. In the reaction above, X is alright. In order to identify the X here, we need to know, we need to compare the masses that we have on the reactant side and the product side here. Okay, now let the atomic mass of X and Z, let the atomic mass and the atomic number of X, let it be Z and Y. Okay, so the atomic mass of this X, okay, is Z, and its atomic number is Y. Now this is an equation, and what we have here is, by the time we add up the atomic masses here, it's more equal to the sum of the atomic masses here. Okay, so if you add the atomic masses here now, the atomic mass is this superscript that I have here. This is the atomic masses, this superscript here. Now on this side, if we add up the atomic masses here, we have 235 plus 1, that is 236. Okay, 236. On the other side, if we add up the atomic mass, okay, this will be 144 plus 90 plus the atomic mass of this x is what we represented it as z. We said let that be z, but because there is 2x here, so that will be 2z. Okay, it will be 2z. So we have 144 plus 90 plus 2z. Okay, and this will be equal to, we can add these two together, 144 plus 90, that will be 234 plus 2z. We cannot add this 2z to it and say 236 for example. No, because they are unlike time. This has z and this doesn't have z, so just leave it as it is like this. Now, following the law of conservation, okay, in this reaction here, the sum of the atomic mass on this side must be equal to the sum of the atomic mass on this side, and the sum of the atomic mass on this side is 236. So you have 236 is equal to the sum on this side, which is 234 plus 2x. Then if you collect like times, that's if you bring this to this side here, this will become 236 minus 234, and so we get 2. So you are going to have 2 is equal to 2z, or 2z is equal to 2. Then we divide both side by 2. If we divide both side by 2, z will be equal to 1. Okay, z will be equal to 1. Now we've done that for the atomic mass, that's the superscript here. We also did the same thing for the atomic number, the subscript that we have here. That is the sum of the atomic numbers here should be equal to the sum of the atomic numbers here. So on this side here we have 92 plus 0, that's 92. While on this side we have 56 plus 36 plus the atomic number here, we said represent that as y, and we have 2 of this thing here, so that will be 2y. So the sum of the atomic number here is going to be 56 plus 36 plus 2y. Okay, 56 plus 36 is equal to 92, so we have 92 plus 2y. Okay, 92. Now, like I said, following the law of conservation of mass, the sum of the atomic number here must be equal to the sum of the atomic number here, and for this side we get 92, for this side I get 92 plus 2y. So we just say 92 is equal to 92 plus 2y. Then if you bring this 92 to this side, this will then become 92 minus 92, that will become a 0. So you are going to have a 0 is equal to 2y, or 2y is equal to 0. If you divide both sides by 2, y will be equal to is 0. Okay, so that means that this substance here, this x here, has an atomic mass of 1 and an atomic number of what, of is 0. Okay, and that is a neutron. That describes a neutron. Okay, the neutron has a mass number of 1, atomic number of 0. You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2, or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram, you could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at scholar.com, or you could also check it out in the video description below. Next question on magnets. To protect a material from the influence of an external magnetic field, the material should be kept in. The material can be kept in a soft iron core, in a soft iron ring rather, to protect it from external magnetic influence. Next question on optics. The refractive index of the material of the medium M in the diagram above is. So the refractive index is equal to sine I over sine R, where I is the angle of incidence and R is the angle of refraction. And you look at the material that we have here. The angle of incidence means the angle between the incident ray, that is the light ray that is coming into the medium, okay, and the normal ray. This is the normal way here. Okay, this is the normal way here, while this is the incident ray. This one that we have inside there, this ray of light, this bent ray of light, is what we call the refracted ray. The angle of incidence is the angle between this incident ray and the normal, which here is 60 degrees. So our I here, angle of incidence is 60. The angle of refraction is going to be the angle between the refracted ray and the normal. Okay, that is the angle between this ray and the normal. And you can see they represented that here as R. They didn't give us the value. Now, if you look at what we have here, this is a right angle because these two lines are perpendicular. Okay, this line here and this line, both of them are perpendicular. That means that the angle between them is 90. Okay, now they now give us a part of the angle as 60. how do we get the remaining angle? We just subtract that 60 from the 90 that is here. So that means that the angle that is supposed to be here is what? Is 30 degree. It is 30 degree, and that will be our angle of refraction, R, which is, so that will be 30 degree. So we then say that our refractive index N is equal to sine 60 degree over sine 30, and sine 60 degree is root 3 over 2 in short form. It is root 3 over 2 divided by sine 30, okay, which is 1 over 2. Now I want to write this out so that you can see how the division here was made to get this solution that we have here. Okay, divided by 1 over 2, so this will be equal to root 3 over 2 times 2 over 1. You may not exactly see what I've been doing, but you see it as a red writing on the screen. So 2 cancel 2, and we are now left with root 3. Okay, so what we have here is an explanation of what we have here. So root 3 over 2 divided by 1 over 2, this becomes multiplication, and you turn this upside down. So we have 2 cancel 2, and we have root 3. Okay, so that's what we have. Next, on heat calorimetry, thermal equilibrium exists between two objects when, that is when their temperature is equal. Okay, thermal equilibrium is said to exist between two objects when their temperature is equal. So when their temperature is equal, then there will be no heat flow from one object to another object. Both of them will be said to be in thermal equilibrium. Next, on waves, which of the following is a characteristic of stationary waves? Stationary waves are formed by two identical waves, okay, that are traveling in opposite direction. Two identical waves, that is two waves that have the same amplitude, the same wavelength and frequency, and they are now moving into in opposite direction. They will produce a stationary wave. Next, on pressure, the height at which the atmosphere ceases to exist is about 80 km. Find the atmospheric pressure at a height of 20 km above the ground level. Alright, so we'll be doing some sort of variation here. Okay, the atmospheric pressure at the ground level, is 760 millimeter mercury. Now if it ceases to exist, okay, 80 km above the ground, it means that the value is going to be dropping progressively from the ground as we go up. Okay, it means that as we are going up, the value is dropping. Okay, now to get a pressure 20 km above the ground, the pressure from 0 to 80 km, is 760, right? Now 20 km above the ground, if you look at 20 km above the ground, if you look at 20 km to 80 km, that's like 1/4. Okay, that's like 1/4 of that height where the pressure ceases to exist. So what we do is, what this will mean is that since the pressure at the ground level is 760, right, and it reduces as you go down from, let's say, 80 km above the ground, it means that if you divide that 760 by 4, okay, you divide 80 by 4, for example, we're going to have 20, so we have 20 20 20 20 down, 20 20 20 20 down. If you divide 760 by 4, you're going to have 190. That means that 190, like the drop in the pressure as you go, okay, as you move up, is 190. It means that from the ground level up 20 km up is going to be what? 190. Sorry, I mean from the top, from that 80 where it ceases to exist, if you go down 20 km, okay, if you go down 20 km, it will be 190. Down 20 km, another 190. That will be like that's 380, right? That's 380. Down again is another 190. That will be 570. Then to the ground level, it will now be what? 760. So if you are going up, if you go up in the reverse order now, if you go up, it means that if you go up a little, it will be what, 570 at that point. Okay, if you go up from 0 to 20, 570. If you go up 380, go up 190. By the time you get to that 80 kilometer, it will then be what, it will be 0. Okay, so that is the range here. So it will be, so as you are going 20 kilometer above the ground, is going to be 570. Next, on its calorimetry, a metal of mass 0.5 kilogram is heated to 100 degrees Celsius and then transferred to a well-lagged calorimeter of its capacity 80 joules per Kelvin, containing water of its capacity 420 joules per Kelvin at 15 degrees Celsius. If the final steady temperature of the mixture is 25 degrees Celsius, find the specific heat capacity of the metal. Okay, so if we neglect heat loss to the environment, let's assume that there is no heat loss to the environment. That means that the heat lost by the metal will be equal to the metal that was introduced into that calorimeter. The heat that will be lost by that metal will be equal to the heat that is gained by the water plus the heat gained by the calorimeter. Okay, the heat gained by the water plus the heat gained by the calorimeter. And heat lost Q is given, or heat generally, quantity of heat Q is equal to mc delta theta. So for the metal, it will be mm. This mm means the mass of the metal, cm means the specific heat capacity of the metal, and delta theta m means the change in temperature of the metal. Okay, for the water, we are going to have mw cw delta delta theta w. Okay, now instead of using mc, we are going to use h, because h is equal to mc. So instead of mmcm, we just use hm, and instead of mwcw, we can use hw. We are going to use it for water here. Okay, so for the water here, just represent this mwcw as hw. So the heat gained by the calorimeter will be equal to mc cc delta theta c, mass of the calorimeter, this mass of the the calorimeter, specific capacity of the calorimeter, delta theta c, the change in temperature of the calorimeter. Okay, now what h denotes is heat capacity. So hm will mean the heat capacity of the metal, hw of the water, hc of the calorimeter. Now since the water and the calorimeter are together, okay, that means that they are going to experience the same temperature change. Okay, the same temperature change. We assume that in the beginning they were in thermal equilibrium, so that will be the final temperature of the mixture, which is 25, minus the initial temperature of the water, okay, which is 15. So you have 25 minus 15, and that is 10. That means that the change in temperature of the water and calorimeter is 15. We then go back to using this formula here. Okay, this that we have here, qm now is this, equal to qw is hw delta theta w plus that of calorimeter qc is equal to hc delta theta w. I did that w because there's the same temperature change, okay, for the water and for the calorimeter. So here we have mass of the water, that is 0.5, times the specific heat capacity, of the metal rather, mass of the metal. Okay, mass of the metal, so that is 0.5 times the specific capacity of the metal in brackets. Okay, the change in temperature of the metal. So the original temperature of the metal was 100 degrees Celsius, and the new temperature, okay, of the mixture containing the metal is 25 degrees Celsius. That means that the metal has lost heat to that mixture, that medium, okay, to that medium in which it was introduced. So the change in its temperature is going to be 75, because it went from 100 to 25. So you have 100 minus 25, that's 75, equal to the heat capacity of water we are given as 420 joules per Kelvin, in brackets the change in temperature of the water, which is 10 here. Okay, let's just skip this, 10, plus the heat capacity of the calorimeter, that's 80 joules per Kelvin, in brackets the change in the temperature, that's 10 as well. So you have this times this is 4200, this times this is 800. Of course, 100 minus 25 is 75. 0.5 times 75 will be 37.5 C. 4200 plus 800 is 5000. To get the value of C, we divide both sides there by 37.5, and that will give us 113.3 joules per kilogram per Kelvin. Okay, now you may wonder that we are using Kelvin here, okay, and that's what's also featured in the solution here, but our temperatures here are given in Celsius, and we did not bother to convert to Kelvin. That is because the change in temperature on the Celsius scale and the Kelvin scale is the same thing, because both of those scales, they have the same interval. So let's say the temperature changed from 30 degrees Celsius to 10 degrees Celsius. Okay, if you look at the change in temperature, that's 30 minus 10, it is 20. That's the magnitude, right? Even if you convert those Celsius to Kelvin, for example, you convert that 30 degrees Celsius to Kelvin, you add 273, that means you have 303. If you convert that 10 to Kelvin, you add 273, that's 283. If you do 303 minus 283, you still get what? You still get that 20. Okay, so the change in temperature on the Celsius and the Kelvin scale is the same thing, and that's why we did not bother to convert again here. Okay, but if you are just using one temperature, okay, I'm not taking the change, then there will be a need to convert, which is what happens when you are dealing with gas loss. Alright, so that's it. Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry, and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post UTME or post JAMB exam, and also for crash courses in physics, chemistry, and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at ScholarFedu. Okay, like and share our content, and visit our website at scholar.com to practice UTM exam and modular quizzes for free. Thank you.